We live in a remarkable age, an age where flight is commonplace. It's hard to imagine a time when the idea of soaring through the skies was nothing more than a dream, a fantasy confined to the realms of imagination and science fiction. Today, millions of people soar through the skies every day, their journeys made possible by the marvel of engineering we call the airplane. These incredible machines have revolutionized the way we travel, shrinking the world and bringing distant lands within our reach. But have you ever stopped to wonder, how do these massive metal birds actually stay aloft? How do they manage to lift off the ground, carrying hundreds of passengers and tons of cargo, and glide effortlessly through the air? How do they defy gravity and carry us safely across continents and oceans? The answer lies in a delicate balance of forces, a fascinating interplay of physics and design that makes flight possible. It's a complex dance of aerodynamics, thrust, lift and drag, all working together in perfect harmony. The wings of an airplane are marvels of engineering, designed to create lift by manipulating the flow of air around them. The shape of the wing, known as an airfoil, is crucial in generating the lift needed to overcome the force of gravity. It's a testament to human ingenuity, a triumph of our understanding of the natural world. From the Wright brothers' first flight at Kitty Hawk to the advanced jetliners of today, the journey of flight has been one of relentless innovation and discovery. In this exploration, we'll unravel the mysteries of flight, delving into the fundamental principles that allow airplanes to grace the heavens. We'll look at the science behind lift, the role of engines in providing thrust, and the importance of aerodynamics in ensuring stability and control. From the elegant curve of a wing, which helps to generate lift by creating a pressure difference between the upper and lower surfaces, to the powerful roar of jet engines, which provide the necessary thrust to propel the airplane forward. Overcoming drag and allowing it to reach incredible speeds will uncover the secrets behind this modern marvel. We'll explore how pilots use ailerons, flaps and rudders to control the airplane's movements, ensuring a smooth and safe flight. So fasten your seatbelts and get ready for takeoff as we embark on a journey to understand the science of flight. We'll dive deep into the world of aviation, exploring the technology, the physics, and the human ingenuity that make it all possible. Whether you're a seasoned traveler or a curious mind, this journey promises to be an enlightening adventure into the skies. To understand how airplanes fly, we must first grasp the concept of the four forces of flight: lift, weight, thrust, and drag. These forces, constantly interacting, determine whether an object stays grounded or takes to the skies. Imagine them as players in a cosmic tug-of-war, each pulling on an airplane with its own unique strength and direction. Lift, as its name suggests, is the upward force that opposes weight. It's what allows an airplane to overcome gravity and climb into the sky. Weight, on the other hand, is the force exerted by gravity pulling the airplane towards the center of the Earth. Thrust is the forward force generated by the airplane's engines that propels it through the air. Finally, drag is the force that resists the airplane's motion through the air. Think of it as air resistance, trying to slow the airplane down. The key to flight lies in generating enough lift to overcome the airplane's weight. This fundamental principle has fascinated humans for centuries, leading to countless innovations and advancements in aviation technology. From the earliest gliders to the most advanced jetliners, the quest to conquer the skies has always hinged on understanding and mastering the forces of lift and gravity. This is where the ingenious design of the wings comes into play. The wings are not just simple flat surfaces, they are marvels of engineering, meticulously crafted to optimize performance and efficiency. Every curve, angle, and material choice is made with the goal of maximizing lift while minimizing drag and weight. An airplane's wings are specially shaped to manipulate the flow of air, creating a difference in air pressure that generates lift. This process is a delicate balance of aerodynamics, requiring precise calculations and testing. Engineers use wind tunnels and computer simulations to refine wing designs, ensuring they perform optimally under various conditions. The shape of an airplane wing is crucial. Known as an airfoil, this shape is designed to create the necessary conditions for lift. The airfoil's geometry is a result of years of research and experimentation, combining both theoretical knowledge and practical insights from countless test flights. It's curved on the upper surface and flatter on the lower surface. This curvature, or camber, is what allows the wing to manipulate the airflow in such a way that lift is generated. The precise degree of curvature can vary depending on the type of aircraft and its intended use, from the gentle curves of a glider to the more pronounced shapes of high-speed jets. This shape, known as an airfoil, forces the air flowing over the top of the wing to travel a longer distance than the air flowing beneath it. This difference in travel distance is what creates the pressure differential needed for lift. The airfoil's design is a perfect example of how form follows function in aviation. Because the air above the wing has to travel farther in the same amount of time, it moves faster. This increase in speed reduces the pressure above the wing, a phenomenon explained by Bernoulli's principle. Faster moving air results in lower pressure, which is a key component in the generation of lift. This faster moving air creates an area of lower pressure above the wing, according to Bernoulli's principle. Bernoulli's principle is a fundamental concept in fluid dynamics, stating that an increase in the speed of a fluid occurs simultaneously with a decrease in pressure. This principle is not only applicable to airfoils, but also to various other aspects of fluid flow in engineering and nature. The higher pressure air beneath the wing then pushes upward, generating lift. This upward force is what counteracts the weight of the airplane, allowing it to rise into the sky. The balance between lift and weight is critical. Too little lift and the airplane cannot take off. Too much and it can become unstable. This upward force is what allows the airplane to overcome gravity and take flight. The journey from the runway to the skies is a testament to human ingenuity and the relentless pursuit of knowledge. Each flight is a culmination of countless hours of design, testing and refinement, all aimed at achieving the perfect balance of forces that make flight possible. As we continue to push the boundaries of aviation, the principles of lift and aerodynamics will remain at the heart of our quest to explore the skies. Section 4, thrust, pushing forward. While lift gets an airplane off the ground, thrust is what keeps it moving forward and counteracts drag. Without thrust, an airplane would not be able to overcome the resistance of the air, known as drag, and would eventually slow down and lose altitude. Thrust is essential for maintaining speed and altitude, and it plays a crucial role in the overall dynamics of flight. This forward force is generated by the airplane's engines, which can be propeller engines or jet engines. Each type of engine has its own unique way of producing thrust, but the end goal is the same: to push the airplane forward through the air. The design and technology behind these engines are marvels of modern engineering, allowing airplanes to travel at incredible speeds and cover vast distances. Propeller engines, like those found on smaller airplanes, work by spinning large propellers at high speeds. These propellers are designed to cut through the air efficiently, creating a difference in air pressure that pulls the airplane forward. The blades of the propeller are shaped like airfoils, similar to the wings of the airplane, and they generate lift in a forward direction, which we call thrust. These propellers act like rotating wings, pulling air in from the front and pushing it out the back, creating thrust. The efficiency of a propeller engine depends on the design of the propeller blades, the speed at which they rotate, and the power of the engine driving them. Propeller engines are typically used in smaller, slower aircraft, but they are highly effective and reliable. Jet engines, on the other hand, generate thrust by sucking in air, mixing it with fuel, and igniting the mixture to create a powerful explosion. This process is known as combustion, and it takes place in the engine's combustion chamber. The high-speed exhaust gases produced by this explosion are expelled out of the back of the engine, generating a tremendous amount of thrust. This explosion forces hot gases out of the back of the engine at high speed, propelling the airplane forward. Jet engines are incredibly powerful and efficient, making them the preferred choice for most commercial and military aircraft. They allow airplanes to reach high speeds and altitudes, making long-distance travel faster and more efficient. The amount of thrust generated by the engines must be greater than the drag acting on the airplane for it to accelerate and maintain a constant speed. Pilots must carefully manage the thrust to ensure the airplane remains stable and on course. This involves adjusting the engine power settings and monitoring the aircraft's performance to achieve the desired speed and altitude. Thrust management is a critical aspect of flying, and it requires skill and precision to master. In summary, thrust is the driving force that propels an airplane forward, overcoming drag and allowing it to maintain speed and altitude. Whether generated by propeller engines or jet engines, thrust is essential for the dynamics of flight, enabling airplanes to travel great distances and reach their destinations safely and efficiently. Section 5. Drag and weight. The constant challenges: drag, the force that resists an airplane's motion through the air, and weight, the force of gravity pulling it down, are constant challenges that must be overcome for flight to occur. These forces are always present, working to slow the airplane down and pull it back to Earth. Drag is influenced by several factors, including the airplane's shape, size, and speed, as well as the density of the air. Streamlining the airplane's design with smooth curves and a sleek profile helps to reduce drag by minimizing air resistance. Weight is determined by the mass of the airplane, including its structure, fuel, passengers, and cargo. Keeping the airplane's weight as low as possible is crucial for fuel efficiency and overall performance. Pause 3S, Section 6, the future of flight. As technology continues to advance, the future of aviation promises to overcome the constant challenges of drag and weight with innovative solutions. Researchers and engineers are exploring new materials such as lightweight composites and advanced alloys to reduce the weight of aircraft without compromising strength and safety. Additionally, aerodynamic designs are becoming more sophisticated, with concepts like blended wing bodies and morphing wings that can adapt their shape in flight to minimize drag. Hybrid and electric propulsion systems are also on the horizon, aiming to reduce the reliance on fossil fuels and decrease the environmental impact of air travel. These systems promise quieter, more efficient flights and could revolutionize the way we think about aviation. The integration of artificial intelligence and automation in aircraft systems is another exciting development. AI can optimize flight paths, manage fuel consumption, and even assist pilots in making real-time decisions during flight, enhancing both safety and efficiency. Looking ahead, the dream of supersonic and hypersonic travel is becoming more of a reality, with experimental aircraft pushing the boundaries of speed and performance. Imagine crossing continents in just a few hours or exploring the edge of space with suborbital flights. Pause 1. Thank you for watching. Please like and subscribe for more videos.